All right. Yeah. Thanks a lot for the invitation. Yeah. So my talk will be about these new physics hints in rare B decays, which have been around now for quite a while. Almost a decade ago that these first anomalies in these rare B decays showed up, and so what I will be doing in this talk is I will try to give you first an overview of those measurements which show disagreement with standard model predictions, and then interpret them in the context of new physics, which type of new physics it could be that is leading to such discrepancies. And in the end, I also have a few slides about some work we did recently in the context of snow mass, where we looked how one could probe new physics that explains the anomalies at a muon collider. Just a very brief introduction, basically a reminder of why rare B decays are interesting and how they probe new physics. So what is shown on this slide here is just a sketch of a B to S mu transition, a rare decay of a B quark to a strange quark and to muons, a flavor changing neutral current transition, which in the standard model happens at the one loop level. Here's one example diagram with a loop of a top quark in a W boson. And one can estimate very roughly what the size of the strength of this transition is by parametrizing it in terms of a four-Fermi contact interaction, so analogous to Fermi decay of let's say a muon. And the corresponding interaction strengths would be estimated here. It goes like 1 over the weak scale squared, and then there's a loop suppression of 1 over 16 pi squared, and there's a suppression by small CKM elements. So overall, it's a strongly suppressed transition in the standard model, and the basic idea is then one tries to measure these type of transitions as precisely as possible. One tries to calculate the standard model prediction as precisely as possible, and one compares those two things. And if they agree, one can get constraints on possible new physics that could show up in those decays, and sort of the model-independent way of parametrizing new physics would be again in terms of a four-Fermi contact interaction, this BS mu interaction, which would be proportional to some Wilson coefficient divided by a new physics scale squared. But doing this comparison between measurement and standard model prediction, one gets information on this combination on new physics couplings and new physics scale. And if there's an anomaly, so if the measurements and the standard model predictions don't agree, then one could get a indirect evidence for a new physics contribution, and one could associate that with a new scale that is given by the new physics. So importantly, if one finds anomalies in these rare B decays, one could establish a new scale in particle physics, which would be a huge thing. And just very roughly estimating which scales one could probe in that way. So basically takes the weak scale multiplied by the square root of a loop factor and CKM matrix elements, and this gets one to around 10 TeV or so. So if one has an order 1 discrepancy between measurement and standard model prediction, the new physics, the generic new physics scale that one could extract by setting the new physics coupling to 1 would be around 10 TeV. So it's conceivable that if such anomalies show up in the data, that whatever new physics is responsible for it has not been seen yet at the LHC. So it could well be that this new physics is outside the reach of the LHC, but it's probably not extremely far above the reach of the LHC. So this 10 TeV number here, it's a high scale, but it's not a scale that is completely impossible to reach with future colliders. So it's actually sort of in a sweet spot that the new physics that could explain these rare B decay anomalies could be outside the reach of the LHC, but within the reach of future colliders. So that's the very basic picture of how these indirect new physics searches in rare B decays work out. On the experimental side, we have a lot of results from LHCb. So the LHC is a P factor. It produces lots and lots of B quarks or B hadrons. In the data that they have collected so far at the LHCb detector, they have more than 10 to the 12 B quarks. So LHCb has actually very unique sensitivity to many rare B decays. They have much more statistics than the B factories, Babar and Bell had. So if it's a decay with a clean signature, they are able to detect this with high precision, and LHCb has made many precision measurements of rare B decays for the first time. And in some of these measurements, in fact, anomalies have shown up. So many of these measurements don't agree very well with standard model predictions. So that I will then discuss now in the next few slides, which of these decays show anomalies and what is the status from the experimental side, and also what is the what might be concerns on this theory side in terms of how precise do we actually know the standard model predictions. So the first decay I want to discuss is arguably the simplest of these flavor changing neutral current rare B decays, which is the decay of a B sub S meson into mu plus mu minus, a purely leptonic decay, bound state of a anti-B quark and a strange quark decaying into mu plus mu minus at the quark level that is exactly this B to S mu transition. And the branching ratio of that decay has been measured by LHCb, by CMS, and also by Atlas. The results are available with a full run-2 data set from all 3 experiments. In the past, they have actually done combinations of their results into a world average, as an official experimental world average. With the full run-2 data that has not been done yet. So what is shown in this plot here is sort of our own naive world average of the existing measurements from Atlas, CMS, and LHCb. So this red region is the world average that we get by combining the measurements, and it's shown in the plane of a branching ratio of B sub S to mu plus mu minus and B0 to mu plus mu minus, which are both measured simultaneously. And this black ellipse here, that is the standard model prediction. The standard model predicts that this B sub S to mu plus mu minus branching ratio is a few times 10 to minus 9, and the B0 to mu plus mu minus branching ratio is around 10 to minus 10. And the measurement is sort of close. It's a bit on the low side in both decays. So there's a 2 sigma-ish tension between standard model and experiment, but that by itself is probably not wouldn't be a big deal. So such a 2 sigma tension wouldn't be very exciting in itself, but as we will see, it fits very nicely into a consistent picture where many other branching ratios also show a similar behavior. One comment here about the standard model prediction, though the hadronic physics, the non-perturbative QCD effects that one needs to know in order to make the prediction for this branching ratio in the standard model. So the hadronic physics is actually under very good control. What one needs to know is the decay constant of the B sub S meson, and this decay constant is can be calculated on the lattice. So lattice QCD calculations exist of this decay constant from various groups, and they all agree with each other, and they quote uncertainties which are the which are very, very small, which are sort of at the percent level or even sub-percent level. So the lattice calculations of this decay constant have reached a very high precision, and there is actually not a concern for the standard model prediction. So the largest uncertainty in the standard model actually comes from CKM matrix input. So one needs to know the CKM matrix element VTS, which due to unitarity is very similar to the CKM matrix element VCB. And there's a sizable uncertainty still in the knowledge of the CKM matrix element. So that gives the uncertainty, the largest uncertainty in the standard model prediction. What is interesting here is that there are different ways to determine the relevant CKM input from other decays, from tree-level decays of B mesons, and this decay matrix element VCB. Actually, there is another anomaly that shows up in the definition of VCB, which is known as the discrepancy between the inclusive and exclusive determination. So that is something where you use either exclusive decays of B mesons, things like B to D L nu or B to D star L nu to determine VCB, or inclusive decays where you have a B meson decaying into anything that contains a charm quark and a lepton and a neutrino. And these two different ways of determine the CKM matrix element VCB, they give slightly different results. And this standard model prediction that is shown here is based on the inclusive determination of VCB, which is a bit larger than the exclusive one. So if you were to use the exclusive value for VCB, the standard model prediction would actually come down quite a bit. And then this 2 sigma tension would be maybe only a 1 sigma tension, so it would essentially disappear completely. So depending on which CKM input you choose, there actually is a bit of wiggle room here and into how big this small tension in the branch initial actually is.
Hey Wolfgang, can I have a few naive questions?
Yeah.
One is, what is this BR bar on the horizontal axis? Is like T at 0 or something?
Yes.
Okay, is T equals 0 like?
Exactly.
Okay.
So,
okay.
Yeah.
I see. But the other question is, okay, of course, I understand the CKM input has uncertainties, but can you say a few more words why the hadronic physics is under good control? You said lattice have done the calculation. The question is, how many groups of lattice people have done that calculation? 2 is, this is a branching fraction. Where does the lattice calculation is useful? Is it useful at determining the form factor so I can calculate the partial width correctly? Or there's another method for me to calculate the total width from measurement or something? This is a very naive question because I don't work in this.
Yeah,
thread.
I mean, so if you look at the B sub S plus or minus decay, it's really just this simple 2-body decay. The only hadronic parameters that you need is the decay constant of the B sub S. So it's just the transition from the B sub S to the vacuum through a quark bilinear, a BS quark bilinear.
Sure.
And that object, is calculated on the lattice. I forget how many groups. I think 3 or 4 groups are doing these calculations, and they all agree fairly well with their results. And they're using different, different formulations of fermions on the lattice, etc. So there, I think there's quite a bit of variety and types of lattice calculations that are done. And as I said, yeah, they all agree with the uncertainties. And if you look, for example, then at this flavor lattice averaging group results, there you see then a list of the various lattice calculations, and then they do their own average of all those calculations, and they give sort of an average value of this decay constant, which has a very small uncertainty. So it seems that this is under very good control.
Okay.
Jen, this coupling doesn't cancel in the branching ratio, because when you divide by the total width of B sub S, right, you use experimentally measured lifetime.
That's right. Yeah. No, I don't expect them to cancel. That's why I asked whether lattice is more on the partial calculation to give me more precise result, and then is the total width is really determined by measurement of lifetime or something. There's no hadronic physics involved in the denominator. Okay.
But I'd like to comment a little bit on inclusive versus exclusive methods, because when together with Misha Schiffman we were involved in this heavy quark calculation, our kind of arguments were that actually on theoretical side, inclusive calculation are much more on theoretical control than exclusive one. So that's why, I mean, it's not the proof that, I mean, that it's a better, but still, if we are going, kind of by theoretical uncertainty there, then it's certainly better on inclusive side.
Yeah.
I mean, so because there are more kind of possibility to change this exclusive determinant, because more stuff you need to kind of assume.
Yeah, that's a good point. I mean, I actually will come back to this inclusive versus exclusive determination in a couple of slides once we talk about other branching ratios. Okay, so that was the B sub s to B plus C minus. So now we go on to 3-body decay. So now we're talking about B mesons going into a kaon or a K star, and then we plus or minus decay. So general semi-leptonic decays, still the same B to S mu transition, but now with some spectator quark on the hadronic side. And there are various measurements again of branching ratios. What is shown in these plots here are measurements of differential branching ratios as a function of Q squared, where Q squared is the invariant mass of the two muons. And this upper left plot here, it's a decay of B plus to K plus mu plus or minus. Then here on the right side we have B0 to K star 0 mu plus or minus, and down here we have B sub S to phi mu plus or minus. They are all based on the same B to S mu transition, just with different spectator quarks. And what one can see here is again that the measurements are all systematically low compared to the standard model predictions, which are shown in these various colored boxes or bands. And here now the standard model predictions have much larger uncertainties than in the purely leptonic decay that we just discussed. Because here you don't only need to know now decay constant, now you really need to know transition form factors, B2K form factors, B2K star, B sub S to phi form factors. And there are also additional sort of non-local effects, non-factorizable effects that one needs to understand, or that one needs to model somehow. So the theory uncertainties here, the standard model predictions, they have much larger uncertainties, and one can even debate of how robust these uncertainties are that are quoted here. One might argue that they are underestimated. There might be additional effects that are not taken into account.
I'm sorry to interrupt, but it's not only form factors, because you have transition in that B to whatever with virtual photon, right? But you also have, say, some stuff like, say, charge radius for B and charge radius for K, right? And it's different story, right? I mean, so in this way, it's not the same as this transition form factor you mentioned.
Yes, absolutely. I mean, transition form factors are one aspect of it, but there are other hadronic effects that are also relevant, and they're not very well understood, I would say. So one can debate of how reliable actually those uncertainties are that are quoted here. But
there's an example without heavy quark. There's this transition without heavy quark, similar kind, when you have, say, strange particle going to the also emitting pair. K goes to pi and a plus or minus, and there you can see similar questions, right? I mean, like here. So this is like a little bit of check a standard model, and here it is where in principle lattice calculation could be useful, right?
Yes. So I mean, lattice calculations do exist for the transition form factors. I don't know to which extent there are lattice calculations beyond that. I'm not aware of any. I think there are some ideas to sort of calculate certain non-local effects, but they're still at the sort of exploratory stage. And
so when what you call prediction, it is still model predictions from analytical QCD, not from the lattice, right?
Yes. So there is modeling that is involved in these predictions.
Okay, thank you.
And on top of all of that, there's again this uncertainty from the CKM matrix elements, which depending on if you use inclusive or exclusive determinations of VCB, again, you can shift the central value of the standard model predictions by quite a bit. So and then depending on what you do exactly, you get oh yeah.
But for the ratio of this decay and without K, this uncertainty would go away.
Yeah. If you take the ratio of the pure leptonic with the semi-leptonic, that's true. Yeah, exactly. There, the CKM drops out, and there you would sort of be then mainly sensitive to these hadronic effects in put study zones. That's an interesting point. I don't think anybody has looked into that. I mean, what is done in what I will explain later is what we are doing is sort of combining all this information in a global fit, and that to some extent is able to then disentangle CKM uncertainties from other hadronic effects. But yeah, looking explicitly at ratios of the types that you suggested, that might be something interesting to do, in fact. Yeah, so then coming back to CKM, this is something that I wanted to briefly mention. When one can, in principle, turn this thing around and say, okay, let's say all these measurements, maybe one can use them to determine a VCB indirectly from these rare decays. So usually what one does is one uses tree-level decays of B mesons to determine VCB and then predict those rare decays. But what happens if one does the opposite? What happens if one tries to determine VCB from those rare decays? And then it's shown in this table here. So here one uses now these rare semi-leptonic decays, B2K mu mu, B2K star mu mu, B sub S to phi mu mu, in different Q-square regions to determine the value for VCB, and then compare it to the direct measurements of VCB from either exclusive B decays or inclusive B decays. And well, because all those measurements are in the previous slide were low compared to standard model predictions and nominal standard model predictions, one finds very low values for VCBs that are preferred by those rare decays. So that's sort of this blue band is the combination that one gets for VCB from all rare decays, and it's significantly low compared to the direct measurements of VCB, in particular this inclusive measurement of VCB, which is sort of I think around 4 sigma above the value that one would get from rare decays. And that's where part of these B anomalies are actually coming from. That is this discrepancy of the inclusive value for VCB and the value of VCBs that one would extract from those rare decays. Overall, I think it's unlikely that VCB is the only responsible for those anomalies. So this inclusive value for VCB seems pretty robust. It also agrees with determinations of CKM matrix elements from meson oscillations, for example. If you look at the B meson mixing, you also can extract a value for VCB, which is very close to the inclusive value. But these rare decays, they all prefer a small VCB. Though arguably VCB is probably not the at least full explanation of where these low branching ratios come from. But it is something to monitor and to keep in mind that CKM input is very important to get precise standard model predictions for all those decay rates. So now we let's move on and try to get to other observables that are sort of independent of this CKM input. And one thing one can do is one can look at angular distributions, in particular of this decay that is shown here. It's a B2K star mu mu decay. So now we have a B meson going into an excited kaon and 2 muons, which then, and this excited kaon then goes into a kaon and a pion. So when there's a 4-body final state, then one can discuss or one can measure the angular distribution of all those decay products. Shown on this slide is an actual event display of how that decay looks like. In the middle here, the primary vertex where the the B is produced and it travels a sizable distance, decays here at the secondary vertex. One sees the two muons and also the pion and the kaon coming all from this secondary vertex here. And then one looks at the angular distribution of the kaon, pion, and the two muons. And one observable that has been that gained quite of attention is this observable called P5 prime, and it is essentially a moment of the B2K star mu angular distribution, and this P5 prime again is measured as a function of Q squared, and it shows again a discrepancy between standard model prediction and measurement. So here now, standard model prediction, these orange boxes here are in this Q square region are quite a bit low compared to the measurement. So it's a 2 to 3 sigma anomaly in a couple of Q square bins, and what is important here is that this measurement has only been done with part of the data sets that LHCb has. So they only use 2006, the run 1 data and 2016 data. They still have data from 2017 and from 2018 to the rest of run 2, and they haven't updated this measurement. But so far, I mean, the anomaly showed up already with old run 1 data, and it was sort of confirmed when they added in the 2016 data. And they also see the anomaly in the case of charged B mesons into charged K stars, where they, however, have much less sensitivity. So there the uncertainties are much larger, but the trend seems to be similar.
Let me just to follow, understand, you call it angular distribution as a way to fix Q square, or, you know, it's not like, because kinematics is kind of is known here, right? But it is just measuring angle to define what is Q square, or what is for?
So what this P5 prime is, it's sort of, you can think of it as a generalized version of a forward-backward asymmetry, right? So I mean, the one of these angular observables that one can look at is a forward-backward asymmetry of, let's say, the mu plus. Does it go in the same or the opposite direction as the K star? And this P5 prime, in some sense, is sort of a generalized version of that, where instead of looking at the angle between the muon and the K star, you look at angles of the kaon with respect to the muon system.
But look, if you decay into, say, excited photon, you know, virtual photon with certain mass and K star, it is two-particle decay. Their kinematics is fixed, right? Then this virtual photon goes to mu plus, mu minus, okay, and it's also kind of standard distribution. So I can understand that this distribution allows you to fix effective mass of mu plus, mu minus pairs. This I can understand, but I do not think there is any kind of anomaly in distribution itself, because all quantum numbers are well known.
You're right. I mean, so what you're looking at is really the B to K star to K pi, and then mu plus, mu minus.
Yeah.
And you know all the quantum numbers of all the particles, so you can write down what is the most generic form that this angular distribution can have. So in total, there are.
Fair to say that
there is no uncertainty there. Yeah.
But you also have a control over the spin of K star, right? From the pair that emerges, right? So something.
No. If I said that K star it is spin 1, what you mean it lost?
Where it's directed, right?
So you are discussing what spin of K star correlated with the spin of virtual photon. There is no uncertainty there.
Right, but in the end you get more information because you get.
No. I'm trying to say that there is no any new parameters associated with angular distribution as compared with a coupling constant enters in this decay. So there is a coupling constant B goes to K star in photon, virtual photon, and there is coupling constant K star goes to K pi. Everything is known. Everything fixed by this constant. So you can write down distribution, but you are not introducing any new parameters.
No, there is information. There's non-trivial information contained in the angular distribution. So if you look at the
non-trivial in the sense of q squared dependence, or non-trivial in terms of adding up new parameters as in addition to coupling constant we mentioned. What is new parameters?
So, I mean, I agree that the angular distribution has a known form. So there are in total there are 3 angles that one can define, 3 independent angles. The angle between the.
I agree. I'm asking differently. I'm asking if I gave you coupling constant b goes to k star for k star gamma star, and I gave you to coupling constant k star goes to k pi, and also electric charge. Do I need some extra constant besides this, or to find the distribution, or that's it?
I'm not exactly sure if I understand the question, but I mean it's more than just the virtual photon which is relevant here. There also this 4 Fermi contact interaction, just BS mu mu contact interaction on top of the BS photon.
BS goes to what?
Say it again.
No, I'm just trying to follow. You have BS, and then BS goes. I thought that K star and photon, right? Kinematically, no, and a virtual photon.
What I'm saying is that
it's not a BS particle. It's a B particle, right? Going to B quark, going to S quark, and mu plus.
No.
Right?
Forget about quarks. I'm talking in terms of in terms of Hadron. You have B state, B meson state, and I have a constant describing B meson state, B meson going to gamma star and K star. How many constants in this world?
What Wolfgang is saying, that there are also contact for interactions that when say Z couples to mu plus mu minus, or electroweak box.
Okay, right? so it's a beyond standard model, because
no, it is standard model. Because
in standard model, Z box you can write down, but it gives you small number. So it's
W box contributes.
Yeah, so the standard model are all of the same order.
W box contribute. I think it would be very small.
No, it's of the same order as the
No. Because transition from B meson to K star and photon, it is the first order in electric charge in electric charge, right? Okay. Everything which involves W and electric constraint G Fermi. So how it could be the same?
Well, it's gonna be G Fermi times m top squared.
Right, but everything here has scale much smaller than massive W, so it's irrelevant.
But the B2K star photon is also suppressed by G Fermi, because you need the W loop to get the flavor change neutral current transition from the B to the K star.
Yeah, but it is overall, right? It is once. This is so you mean that this is W exchange for sure? I agree, right? That it is there, but it is this sentence, but it is overall G Fermi. We are talking about additional part. So you are saying that even this transition could be not due to W, but it could not be. There is no neutral current, for example. So Z is not involved.
What I'm saying is that there is the B2K star gamma contribution that you are mentioning, but there are these additional B2K star mu plus mu minus from a contact interaction, which are of the same order in the electroweak interactions, and they all contribute roughly at the same level.
I see. Contact interaction, it is the same as to say that you have something like d mu f mu, right? So you're like monopole photon. It would be the same as contact interaction. No, I mean, so you are saying that that in this way, but so it would be still would be a part of electromagnetic interaction, but in electromagnetic interaction there is a part which kind of shrinks. You see, because if you have something proportional to q squared, it cancel out photon 1 over q squared.
That's part of it. Yes, that is part of it. And there's also
what else? What else? This is there. I agree.
As Maxime mentioned, instead of the photon, you have a Z boson, for example. Then it would be extra q squared divided by mw squared. This I would not take.
No, because the current under Z is not conserved, Arkady. So therefore, it would be G Fermi squared indeed, but it will be multiplied by m top squared as always happens.
But multiply, but there is no MW in the denominator. How you get it? Your energy is
sorry? M top squared. M top, it's a loop factor, right? So M top squared.
No, why loop? Why loop factor? No, if it would be loop correction, I agree that loop correction could be over the alpha, but they would be suppressed by alpha at least.
No.
If the process exists without loop, then correction due to the loop is proportional to alpha.
But the process with a photon is, of course, also a loop level.
Why?
Because you need a flavor changing neutral current transition from B to K and the gamma star in the gamma star. So it's already a loop factor. So if you count the couplings, it's the same thing.
Okay, I agree, right? But then it means that this coupling constant I'm talking about would be in the loop order. I accept this, yeah. But still would be coupling constant, which you can phenologically describe as vertex B goes to K star and gamma star. This is generic. Which include your loop factor if you like. No, I mean,
but
I
it's
can.
on the part, right? So
so you are saying that what you are saying means that how many vertices B goes to K star, gamma star, I can write, including the mu F mu.
Not only gamma star, because
local terms and then the mu F mu it is the same statement. No, I mean,
I'm saying that. Even if I
no, I agree. I agree that this you can, but no, I'm not insisting that it should be a particular monopole photon. I was just mentioning that monopole photon in terms of angular distribution would be the same. But you can say that it is anyway. It's not. No, I mean, you see, it's equivalent that if you have this vertex where mu plus mu minus coupled to directly to this one, not to the photon, it's okay, right? So I mean, it could be, but still it would be like another coupling constant in the vertex B goes to mu plus mu minus and K star, right?
Right.
Yes.
Well, I just wanna add that if you take B to K star nu bar that doesn't have any photons, right? It has
I agree.
It's very same branching ratio.
Right. So you can write this vertex, and I agree that it should not be particular photon. No, I agree with this. Yeah.
And then coming back to this annular distribution, what it does in some sense is to tell you the relative size of the various contributions. So how much of the gamma star is there, how much of the actual contact interaction, which are the chirality, what is the chirality structure of those contact interactions, etc. That will all influence what the angular distribution of the decay product is. All right.
But this calculation is not kind of sufficiently cumbersome, right?
That is also still a complicated calculation. You run into the trouble of having to model certain hadronic effects, and it's not very well understood how to do that. The only the advantage of it is that you got rid of these dependent on CKM matrix elements. So the angular distribution doesn't care about the prefactor, about the CKM prefactor that you have in the branching ratio. but you still have to deal with all the hadronic physics that might not be very well understood. So if you want to get rid also of the hadronic physics, then the observables that people came up with are these Lepton flavor universality ratios. So now you're looking for ratios of branching ratios with either muons or electrons in the final state. So RK and RK star, these are ratio observables, ratio of a branching ratio of B to K mu mu over B to K EE or B to K star mu mu or B to K star EE. In the standard model, they are now predicted to be 1 with very high precision. I mean, individually, these branching ratios, they have large uncertainties, and there's this modeling uncertainty from low energy QCD. But in the ratio, all those uncertainties drop out with very, very high precision. So the standard model predicts that these ratios should be 1, and people estimate that uncertainty should be maybe at the % level or so. And experimentally, what is found is that these ratios tend to be all below 1, and significantly so. So the most precise measurement, which is now which was updated a year ago or so with the full run 2 data set, is the measurement of RK plus in a Q-square region from 1 to 6 GeV squared. And that's around 0.85 with a 5% uncertainty, with a 3 sigma discrepancy with respect to the standard model prediction. And all these other R ratios, they're also below 1 at the level of, I don't know, 20 to 30% or so, with much larger uncertainties. Several of them are sort of a couple of them are in this 2.5 sigma regime, and the others in 1.5 or 1 sigma only. Interestingly, these RK star measurements, they are only done with the run 1 data. So there will be very interesting to see updates with the full run 2 data set as well. But if those results grow in significance with more data, then those would be a very clear indication of a new physics effect, because there is very little you can do with standard model uncertainties here. Yeah, so just to summarize, what could those various things be? So we talked about the B sub S to plus or minus rate, which is a bit low. It could be a statistical fluctuation. It's only a 2 sigma effect. There could be parametric uncertainties. I mentioned the CKM input, VCB, that one needs to know. It probably is not due to hadronic effects. This is something that we had discussed, and we only need the decay constant there, or it could be new physics. For the semi-leptonic rates, the B to K mu mu, B to K star mu mu, B sub S to phi mu mu branching ratios, there again individually they're sort of at the 2 sigma, maybe 3 sigma level. They could all be statistical fluctuations. It could be due, partly at least, due to parametric uncertainties, VCB input. They could be due to hadronic effects, or they could be new physics. The angular observables, so they have been constructed such that the parametric uncertainties from CKM input, they drop out, but they still could be statistical fluctuations. They could be hadronic effects, or they could be new physics. And this Lepton flavor universality ratios, well, there from the series side, when it's now pretty robust, it cannot be any parametric uncertainty.
One more quantity which could be, I'm not sure, could be in principle relevant, is correlation of polarization of mu, because you see, because it could be like a vector current, or it could be not like a scalar current or whatever, right?
Yes. If one could measure the polarization of the muons, that would be interesting. But that's I think at least at LHCb, I don't think they can do that, and also I think at the B factors they wouldn't be able to do that. But yeah, in principle, the muon polarization contains interesting information, and if one were to access that, this would give interesting hints of which type of new physics this could be.
It's very hard. You first gotta like stop muons.
Yeah.
No, it's difficult to measure, right? But for example, this angular distribution measurement and this one could be in certain way related, right? Because when you are saying which type of current they enter, so it influences.
Yes, definitely. Another way to summarize the situation is this plot here, which I like to show usually in this type of talks, where you plot the significance of the discrepancy on the x-axis, and then sort of the relevance of hadronic effects on the y-axis. So the higher you are in this plot, the least you have to worry about hadronic effects. So the cleaner the actual theory predictions are, and arguably the highest in this ranking would be this RK and RK star lepton flavor universality ratios, which are technically very clean. And then the B sub S plus minus branching ratio is also still relatively clean. And then the angled observers are a bit less clean. And then the semi-leptonic branching ratios, they are sort of the least clean from the series side. So in some sense, these discrepancies are the least trustworthy. Sort of to gauge. Another thing I should mention, there are also these hints for lepton flavor universality violation in charged current decays, B2 charm L nu decays. These are these RD and RD star ratios, where you compare decays into taus with decays into light leptons, and also there one sees discrepancies. So these RD and RD star ratios, they're also off from standard model predictions by 2.5 sigma or so. But they are not necessarily related to all these anomalies that I have been discussing in the rare decays, so in the B2S LL flavor change in little current decays. Sort of to gauge sort of the scale on the y-axis, I put here also the G-2 of the muon, which I think is sort of somewhere in the middle here, though I don't think G-2 is as clean as RK and RK star, but it's certainly cleaner than these semi-leptonic branching ratios, and angled observers in B2K star and mu is P5 prime, and the these are plus minus branching ratios are probably somewhere at the same level as G-2 of the muon, I would say. All right, that was the sort of the description of the anomalies, and I think I'm almost out of time, so I should probably speed up a bit and talk a bit about how to address those anomalies. So the basic setup goes in various steps. So once you have identified a set of anomalies, the first thing one usually does is to try to describe them in a model independent way, or in a as model independent way as possible. One tries to parameterize the new physics in an effective field theory, for example in SMEFT, or if you go to low energies where the B decays actually happen, you could do something which is called left, the low energy EFT, which doesn't care about electroweak symmetry. And then one needs to make only minimal assumptions for that to be applicable. Basic assumption is that the new physics is heavy compared to the decaying B mesons, and then this description will work. And then on top of that, one can start to construct simplified models where one introduces a minimal set of new physics particles, maybe a leptoquark or a Z-prime gauge boson, which then could realize some of these effective interactions that one has identified in the first step. And then ultimately, we would like to embed that into a sort of a UV-complete motivated model, which not only addresses those rare B anomalies, but also tries to answer other open questions in particle physics, the hierarchy problem, maybe the standard model flavor puzzle, maybe it has a dark matter candidate or things like that. But I will mainly focus now here on this first step, on this sort of model independent approach to the anomalies. And the setup is very well established. So one writes down an effective Hamiltonian, which contains dimension 6 interactions, effective interactions of dimension 6, which come with Wilson coefficients that can contribute to this B2S LL transitions. One can have modifications to the B2S gamma interaction, so these dipole type interactions with Wilson coefficients that are usually called C7 and C7 prime, depending on if it's a left or right-handed B quark in this operator. And then one has various types of 4 Fermi contact interactions between B quarks, strange quarks, and two muons. And then depending on what the chirality structure is, the Wilson coefficients are called C9 or C9 prime, C10 or C10 prime, or then a scalar version here, CS or CS prime. And the various decay modes that we have discussed, plus other decay modes like the B2S gamma decays that we can also look at, they have then characteristic dependence on the Wilson coefficients of these new interactions that one is switching on. And so what one then usually does is to do global fits, where it includes all the information of all those rare decays in order to understand if there's any high dimensional operator, if there's any of these Wilson coefficients which actually leads to a better description of the data in a global sense. So it can explain the anomalies, but at the same time it doesn't introduce other anomalies in observables that actually do agree with standard model predictions. And so this sort of business of doing global fits has now become sort of a small industry. There are several groups who do these type of fits. And overall, there's actually pretty good agreement between the various groups, and the results that one gets are actually pretty consistent across the various groups. And I will show that actually in a few slides. Here I'm just showing one plot from the last paper I had about these global fits from March last year. One way to sort of visualize the results is in two-dimensional planes of Wilson coefficients. What is shown here in this plot is the Wilson coefficient C9 versus C10. And here's again the definition of what those Wilson coefficients are. These are the Wilson coefficients of these contact interactions, four-Fermi contact interactions, which contain a left-handed current for the B2S transition, and then either a vector current for the muons or an axial vector current for the muons. And then one can plot in that plane what is the preferred region of parameter space, taking into account a certain subset of experimental results. If one only takes into account the Lepton flavor universality ratios, RK and RK star, one gets sort of a very broad, approximately diagonal band here in this parameter space. So one sort of prefers non-standard C10, but also there's a large degeneracy. This sort of diagonal band that one gets from RK and RK star measurements. And yeah, so the standard model here is at 0, 0. So this what is plotted here really is the new physics contribution to those Wilson coefficients. And already with these RK and RK star measurements, one is pretty significantly away from the standard model here at 0, 0. And then one can add in other information. One can add in the B sub S to plus minus branching ratio, which again shows a slight preference for non-standard value of C10. So this is yellow band here. One can add in all the other B2S mu observables, so the P5 prime and the semi-leptonic branching ratios, making certain assumptions about the uncertainties of the standard model prediction. And if one does that, overall one gets this red blob here as the best fit region of a global fit of all those rare B decay data, and one gets a certain best fit point here. The one thing, just to understand what those numbers mean, in this normalization, the standard model values for those Wilson coefficients are around 4. So it's something like a 15% new physics effect in C9, for example.
Is it a huge improvement in chi-squared, or?
Yes, it's a very huge improvement in chi-squared. So it's a difference in chi-squared of around 30 or so. So it's a pretty big delta chi-squared that you get. Then the question becomes, how do you interpret that very big delta chi-squared? And that's a bit of a separate question, but at face value, you do much better than the standard model. One thing to mention here is what is shown here is new physics in the muons. You don't necessarily have to do that. So if you're really only interested in RK and RK star, and you say that these other processes, all these B2S mu transitions, they are subject to large theory uncertainties, and you maybe don't trust them, then you can explain RK and RK star also with new physics in the electrons. So instead of suppressing the branching ratios into muons, you can enhance the branching ratio into electrons, and also get a good fit of the data of RK and RK star. Of course, you don't explain these other anomalies because you might argue that they are not even anomalies, that they are maybe due to underestimated standard model uncertainties. Yeah, so as I said before, so there are various groups who could do these fits, and actually it was a workshop last year at CERN where several groups came together and sort of carefully compared their approaches and tried to understand the different approaches, the differences, and the that one finds in the results. And overall, as I said, there's actually pretty good agreement between those different groups, and this is shown, for example, in these two plots here. There's now, instead of doing this two-dimensional fitting, one only switches on one operator at a time, and just to have a simple comparison. And overall, there's a pretty good agreement between the different groups. So all groups agree that there is, for example, a very strong preference for a new physics contribution to this C9 Wilson coefficient. The precise size of the new physics contribution is somewhat different for the various groups, but overall there's a clear agreement that there is a preference for a non-standard C9. And again, these poles that one gets, so the difference in delta chi, the delta chi-squared between these best fit points, fit points in the new physics scenario and the standard model are very large, so more than 5 sigma, which of course is not the global significance of all these anomalies.
Sorry, what's the standard model value for C9?
C9 is around +4 in the standard model.
Okay.
Yeah, so sort of a minus 20% new physics effect here in C9. And you can do something similar for C9 equals minus C10. That would correspond to a left-handed current for the muons, and there one finds similar results. So both of those scenarios, they give a very good fit of the data. In both cases, you get these pulls of more than 5 sigma.
Sorry, so I had a question. So what's the scale of the new physics, or does it not enter here? Does it cancel in the ratios? Is that right?
No, the new physics scale is a relevant thing. So
you chose it to be some value here, right?
Correct. So the way this is done, I can go back to this slide here. So the way it's done, you factor out sort of the same prefactors that you also expect in the standard model. So you have a Fermi constant and CKM matrix elements and the loop factor.
I see. So it's normalized to Fermi. Okay, sorry, you said that before.
Yeah, Fermi times loop factor and CKM. So if you actually put in a number here, it's around I think 30 TeV.
30 TeV.
Yeah,
I see.
Yeah.
Thanks.
And so people who try to assign an actual global significance to all those anomalies, they find something like a 4 sigma global significance if you combine those anomalies, and that's mainly driven by these Lepton flavor universality ratios. If we just naively combine the significance of those handful of 3 and 2 sigmas in RK and RK star, we do get roughly this 4.3 sigma that is also found by in this paper here, who looked into also things like Lugelsberg effects in series space to some extent. Here the same comparison now in 2D. So again, this C9 versus C10 plots. What is interesting here on the right hand side, this right hand plot that shows the best fit regions that the various groups are getting if one only includes, let's say, theoretically clean observers. So only this Lepton flavor universality ratios and the B sub S to be plus or minus branching ratio. And in that case, there's perfect agreement between the different groups. So there's perfect overlap of these best fit regions. Once one includes also the other observers, where then standard model uncertainties play a much bigger role, where the modeling of hadronic effects plays a bigger role, then one sees slight differences, and then those are understood based on the different treatment of standard model uncertainties and the hadronic modeling that goes into the various global fits that have been done. But if one focuses on the theoretically clean things, there's a perfect agreement between the different groups. Based on the on these global fits, one can then make predictions for other observers which have not been measured yet, and that one example is shown here. Predictions for various of these lepton flavor universality ratios which have not been measured yet. So they're all predicted to be around 0.8 or so, which is mainly driven by this precise measurement of RK star that already exists. Though all the other R ratios, all these other lepton flavor universality ratios are expected to line up with that measurement, and it will be very interesting to see how the future results from LHCb on all those ratios will turn out in this plot here. Yeah, now coming back to the scale, do I actually have this slide here, which exactly tries to answer that question. What is the new physics scale that is related to those anomalies? The scale itself, of course, that you extract depends on the assumptions you make about the couplings, the new physics couplings. But in this generic scenario where you say that the order 1 coupling of new physics, and you just parameterize the effect as a 1 over new physics scale squared, then the scale is actually 35 TeV. And if you put in a CKM suppression, then you go down to 7 TeV. If you put a loop suppression, you're 3 TeV. If you put CKM and loop suppression, you're a few hundred GeV. If you sort of go all the way up to a perturbative unitarity bound, if you put a new physics coupling of 4 pi, you could push the scale to around 120 TeV. So in principle, there's a broad range of new physics scales that can work, because in this indirect way of looking for new physics in rare B decays, you're really only sensitive to the coupling over scale. And so depending on which assumptions you make about the coupling, you get a broad range of possible scales. The generic scale turns out to be this 35 TeV. Now, what are the prospects of sorting this out? So at LHCb, one can actually expect in the future really precision measurements of these lepton flavor universality ratios. So they're shown in this plot here is the expected precision on RK and RK star with more and more data. And the claim is that sort of at the end of the high luminosity run of the LHC, they will have sort of 1% or even sub% precision on RK and RK star, which would then be really extremely high precision. And if the central value stays where it is now, one would have an extremely high significance of a non-standard effect. Also, BEL2 should be able to say something about RK and RK star. The once they do get higher luminosities, they also should be able to measure that with sort of a few percent precision, and that would be also very useful. One thing to consider here is that plot, I think, was done before COVID, so everything should be moved a couple of years to the right here. So in particular, these BEL2 projections, they probably have to be moved quite a bit. I don't expect that BEL2 will have this few percent level precision in the next few years. So they might start to say something at the time scale of maybe 3 to 4 years or so, but to get really to this high precision, one probably needs to wait still until the end of the decade, I would say.
BL is going to stop at June for more than a year.
Yes, exactly. So far they haven't yet reached the same luminosity as BEL, and yeah, as you say, they will go into a shutdown phase now for a year or so, and then they will restart and with data taking, and to reach sort of their final luminosity goal of 15 with autobahn will take quite a while, I think. So this 2025 here is very optimistic as far as I understand.
Is it machine related or detector related?
The shutdown?
Yes.
I actually don't know.
I know why shut down, because the price of electricity went up, and they are not going to supply electricity for the year.
Yeah, that's true. that's why they do sort of this early shutdown. I think originally they planned to run for longer before they do the shutdown, but yeah, I think it's a funding issue that they have to sort of do this early shutdown or shut down earlier than they had originally planned.
My God.
Yeah, but eventually it should be possible to sort it out with the data that is expected at the LHC and at Bell 2. I think I'm completely out of time. I had a few slides about muon colliders. So let me might skip this intro about muon colliders. Just want to say a few things. So if you believe that there is indeed a new physics in this B to S mu transition, if you think that there is indeed a Wilson coefficient, let's say C9 or C10, that explains these anomalies, then you can put that operator into a muon collider and have a non-standard B and strange jet production in mu plus or minus collisions. So you have mu plus or minus going to bottom and strange. And of course, because it's a 4 Fermi contact interaction, a dimension 6 operator, if that description in terms of a dimension 6 operator continues to hold also at high energies, then at the muon collider you would get an increase of that cross section with the center of mass energy of the muon collider, while the standard model backgrounds, they tend to fall off with the center of mass energy. So if you go to a high energy muon collider, you should be able to see this non-standard production of bottom jets and strange jets. In principle, you can also get access to the chirality structure of that interaction by measuring the forward-backward asymmetry of the B jet in this type of events. For that, however, you need charge tagging. So you need to understand if it was a B jet or an anti-B jet that was produced, because the forward-backward asymmetry comes in with different signs. So if you just add those events up, you get 0 as a forward-backward asymmetry. You need to be able to tag the charge of the B jet to measure this forward-backward asymmetry. Yeah, here's one slide about possible backgrounds. Again, as I said before, most of the standard model backgrounds, they just fall off with the center of mass energy. The main background actually is coming from just dijet events where you mistag one of the jets as a B jet. But sort of at a center of mass energy of around 10 TeV, the signal cross section, which is this red line here, and this dominant standard model background, they cross. So for a 10 TeV muon collider, you would have a ratio of signal over background of order 1, and you should be able to see this non-standard production of B and strange jets. And then one can sort of project the sensitivity of a muon collider into that plane of C9 versus C10. So just measuring the rate would give you this green circle here on the left. This plot is done with 1 inverse autobahn. On the right, the plot is done with a integrated luminosity at a muon collider of 10 inverse autobahn, which is sort of the one of these benchmark scenarios that was used for the muon collider studies at SNOMAS. And one sees that, but can actually get a very strong constraint, a very precise measurement of C9 and C10 from a muon collider. This dashed contours here are the current best fit ranges if you only take into account the clean observables, the RK and RK star measurement, and the vis-a-vis plus or minus branching ratio that I had on an earlier slide. And this sort of more narrow dashed region here is what one would expect at after the high luminosity run of the LHC. So then, if you take into account the expected position you have from LHCb on RK and RK star and vis-a-vis plus or minus, and if it is indeed new physics that sits in those rare decays, then you will be able to constrain the parameter space to that dashed ellipse here, and then a muon collider would have very comparable sensitivities and should then see the same thing and could be able to constrain it even slightly better than the B decay results from LHCb.
Hi, Wolfgang. Should I be surprised that the muon collider is such a powerful machine were only comparable to the projection, projection? We're slightly better, right, with muon collider, but not much.
Yeah, I mean the main thing is the backgrounds that you have to be able to understand, I guess, and it's really this QQ bar background which is pretty large, and it will depend on how well you can actually reject this QQ bar background. So we made some assumptions about B tagging efficiencies and light and sort of mistag rates for of light jets being identified as B jets, which we assume to be comparable to what people can do now at the LHC, and then you get this result here. So if B tagging at a muon collider turns out to be sort of much better than what is done now at the LHC, one could get better sensitivity at the muon collider than what we show.
Yeah. Also, the operator you're trying to probe, the process you're trying to probe is the operator squared, right? So there's no the one interference decouples very quickly when your momentum is high. So I guess that's another price you have to.
Yes. Yes.
Okay. Thanks.
Yeah, and this scenario is that, again, one thing one has to keep in mind here is that only holds if at this 10 TeV muon collider, the description of the physics in terms of a contact interaction is still valid. And that's not necessarily the case. It might be that there are some leptoquarks or Z prime gauge bosons which actually produce that operator, which are much lighter. But in that case, you would sort of directly see those new physics particles at a muon collider, and there are studies of that type which look at Z prime models and leptoquark models, and which find that you can see them at the muon collider with high significance.
Thanks.
And yeah, so that's it. Here's my summary. So I discussed these B anomalies, these B decay results. They continue to show intriguing discrepancies with standard model predictions, and it's really the focus in the coming years will probably be on this lepton flavor universality ratios. If there the anomalies grow with more statistics, then those should be a clear indication of new physics. And looking sort of in the very far future, if we ever get a muon collider, a 10 TeV muon collider could conclusively test those explanations of in terms of Fermi contact interactions. And yeah, whatever is going on here, it will be very interesting to see what comes up in the next round of updates. And yeah, as we said at the beginning, it would have been nice to see new results at Morio already this week or last week, but hopefully in the not too far future, LHCb will show some updates in this regard. All right, thank you.
All right, thanks a lot. Thanks a lot for the very nice talk. So let's thank Wolfgang. Any questions from the audience?
Yeah, so you didn't say anything about new physics or new models or the models. So what in your opinion is like the most compelling model to explain?
Good. Yeah. So with Maxime several years ago, we had written down a simple model, sort of a simplified model where you have a Z prime boson which is based on gauging muon number minus tau number.
I see.
So that gives you the coupling to the muons and no couplings to electrons. So that gives very naturally this lepton flavor non-universal aspect. And then you need some ingredients in the model that generates the flavor changing coupling on the quark side. So the coupling of the Z prime to B quarks and strange quarks. And one way to do that is the way we had done that is by introducing additional heavy vector-like quarks, which are charged under L mu minus L tau, which then mix with the standard model quarks. And that is one setup that works, which still works, though after many years that we have written down this model, the model still survives.
So in your opinion, that's the best one then?
It's I don't know if it's the best one. I think it's a sort of one of the simplest scenarios that one can write down, which works. And
you see, when you say simplest, it's just minimal. It's just that you don't need many parts to it. I see.
Yeah.
It also depends on how many things you want to fill with one model, right? So Wolfgang avoided talking about anomalies in the charge channel, So which you cannot explain with that, right?
Uh-huh.
So Wolfgang, maybe you can say a couple of sentences or more about what's up with this comparing tau with mu e in the B decays in the charge channel.
Yes, yes. So I had briefly mentioned those lepton flavor universality ratios in the charged current decay, so B to charm tau nu over B to charm mu nu or E nu. And for those anomalies, really the only model that works are leptoquarks. So there are, I think, a couple of leptoquark models which in principle can explain those. There is one leptoquark which simultaneously can explain those charged current lepton flavor universality ratios and the neutral current anomalies that I have been discussing in this talk. So that is what is known as the U1 vector leptoquark, which can be embedded into a Patti-Salam gauge group. So this U1 leptoquark can be a Patti-Salam gauge boson. The problem is that the simplest scenario where you just have a Patti-Salam gauge group and then you set things up such that you have all these flavor changing or that you have the corresponding couplings of this leptoquark that is completely excluded by things like K2 mu E. That gives very, very strong constraints on such leptoquarks. So the scenario that people then look at is where you have what they call Patti-Salam cubed, where you have 3 copies of Patti-Salam, one for each generation. So you have one Patti-Salam gauge group for the third generation, one for the second generation, one for the first generation. You make the corresponding new physics scale for the first and second generation very heavy. So what is left at low energies is this one U1 leptoquark, which likes to couple mainly to third generation, and then you have some mixing, which also introduces some small coupling to the second and the first generation. And so that these are models that have been worked out in quite some detail by Gino Isidori and company. And yeah, so they are probably the most fleshed out UV complete models of set types that are around.
Was there any recent updates that kind of weakened the anomaly there, or I just misremember?
So there haven't been much updates since a few years on RD and RD star. So the latest update was from Bell, and I think that was already at least 2 years ago, or maybe even 3. And that one was much closer to the standard model prediction than the earlier measurements. So early on, also the significance of RD and RD star was, I think, above 4 sigma. If you do sort of a world average now of the all existing measurements, it's more like 3 sigma now, and it's mainly driven by the Babar result. So the first result on RD and RD star that came out was from Babar, and that was sort of way off, much very far away from the standard model, and that is still the one which is largely driving this anomalies until now.
But have people also tried SUSY or composite Higgs models as well?
Yeah, so for SUSY, sort of if you take the MSSM, there's very little you can do. In particular, if you want to explain lepton flavor universality violation, the only way you would get that from SUSY would be if you have I think you need some box diagrams with leptons inside, and you have sort of a very light muon and a very heavy selectron or something like that, and the flavor violation that you need needs to be really huge, and it's very difficult to get the effect in these rare decays without getting into trouble with things like with constraints from B mixing, for example. And at the same time, you also have to be worried about direct searches for SUSY particles. Everything needs to be pretty light in order to get the effect in the rare B decays. So SUSY, I think, doesn't really work. Composite models, people looked into that. Then you can have, again, this similar to for example, Z prime models, Z prime models, where you would need then, for example, a right-handed muon, which is a high degree of compositeness. So you have a row of the composite sector which likes to couple to muons, and then again has some flavor changing coupling on the quark side, and that can work as sort of a UV completion of a Z prime model explanation of the rare B decay anomalies. And people also looked into sort of composite versions of leptoquarks, where for some reason the composite sector contains states which resemble these leptoquark states, and in that way explain the anomalies.
I see. Yes, that sounds pretty baroque then for these kind of models.
Yeah.
And so returning to this, there may be one last question from my side. Returning to this issue that it could be an experimental issue, what are the current thinking, or is there any possibility that somehow like they're wrong with efficiencies and so on? I understand that for the mu and E channels for universality, they take double ratios, so that kind of with J size, right? So the efficiency drop out. But yeah, is there any suspicion what could go wrong?
I don't know of any lead or so of what could be going wrong. There was end of last year, there was a paper by Dean Robinson who had some idea of what might be going wrong. So his idea was that when they measure the B2K EE, they have, of course, to deal with Bremsstrahlung from the electrons, and they have some Bremsstrahlung recovery algorithm which sort of associates photons that they also have in their events to electrons. And his idea was that if you have now in these events additional pi zeros, and if these pi zeros came to gamma gamma, and now if this Bremsstrahlung recovery algorithm takes photons from these pi zeros and mistakenly associates them also to electrons, that can change their results for the B2K-EE branching ratio. But they actually, LHCb did look into that, and they found that it is only a per mil level effect in the end. So this was one thing that I found was an interesting idea, which might have had some impact, but it turned out to be also not relevant. So I don't know of any good explanation of what could be going wrong from the experimental side.
Do you know if they follow our suggestion and look for something like lepton universality in the channels where weak decays are not important? Something like we're suggesting phi, right? Or
yes,
is this doable at all?
Yes, it is doable. I mean, I did talk with them about that already several years ago, and they said that they are looking into that, and they want to do this lepton flavor universality of phi decays, for example. But I haven't heard anything recently or what the stage of that is.
They don't like it because it's sort of implication is that they might be making a mistake, right? And they're quite nervous about it.
Yeah. I mean the argument why already now everything should be completely robust and one doesn't expect anything to go wrong is that whatever other probes you look at, the kinematic distribution in terms of momenta and an angular distribution in the detector is more or less the same. So the fact that you have different Q-square ranges that you're trying to probe lepton flavor universality doesn't really matter for them, because in the detector it all more or less looks the same.
My statement to this is that if you can show that the universality is preserved where it should be preserved, right? It would be just strengthening your main main statement, right? But
yeah.
somehow no was never followed up.
Yeah, I agree. It would be something very interesting for them to do. And yeah, talking to them, they should be able to do that. And the ones I talked to, they seem to be interested in looking into that, but then they apparently haven't really followed up on that.
Okay, thanks. Any more questions from the audience? All right, let's thank Wolfgang again for the very nice talk. Thank you.
Sure.
All right.